Okay, let's jump right in. Just take a look around you for a second. You're surrounded by metals and nonmetals. You've got your phone, a bridge, maybe a coin in your pocket, and then you've got a plastic bottle, the glass in your window, or the graphite in a pencil. They feel different, they act different, and today we're going to uncover the fundamental secret that separates these two massive families of materials. It really all starts with a super simple question. Think about it. Why can you bend a metal paperclip back and forth no problem, but if you try that with the lead in a pencil, snap, it just breaks. One is flexible, the other is brittle. So why is that? This simple, everyday observation is actually a clue to a much, much deeper story. And the answer to that why, the reason for all these huge differences we can see and feel, isn't something you can spot with the naked eye. We have to go deeper, way deeper. We have to zoom all the way into the invisible world of atoms. That's where the real action is happening. All right, so our investigation begins with the most obvious clues, the physical properties. These are the classic traits that make us look at something and instantly go, yep, that's a metal.
First up is malleability. Now, that's just a fancy word for being able to be hammered or pressed into super thin sheets without breaking. And some metals are absolutely incredible at this. Gold and silver, they're the champions. You can hammer gold into sheets so thin, they're practically transparent.
And right alongside that, you've got ductility. This is the ability to be stretched or pulled out into a thin wire. It's because of ductility that we have things like copper wiring carrying electricity all through our homes and our cities. And to put that property into perspective, get this. Just 1 single gram of gold, that's about the weight of a paperclip, can be stretched into a wire that's 2 kilometers long. That is just an incredible level of flexibility, and it's a huge reason why metals are so useful. And of course, the list of clues goes on, right? Metals have that signature shine, what we call luster. They're fantastic conductors, which is why your cooking pots are metal. They're sonorous, they make a ringing sound when you hit them. That's why school bells are made of metal. And as a rule, they tend to be hard and have really high melting points. But here's the twist. If we only go by these physical rules, things start to get a little weird. For instance, some metals, like sodium, are so soft you can literally cut them with a knife. And then you have iodine, which is a nonmetal, but it's shiny and lustrous. So what does that tell us? It tells us these surface-level clues aren't enough. To get the real answer, we have to go deeper. So, if the surface clues can be a bit misleading, where does the real secret lie? Well, it's in their chemical properties. And it all comes down to an invisible dance performed by these tiny little particles called electrons. This is where the magic happens. The driving force behind pretty much all of chemistry is one simple goal: stability. Think of an atom's electrons as being in layers or shells. An atom is happiest, it's most stable, when its outermost shell is completely full. And atoms will do almost anything, give away, take, or share electrons, just to get that stable, full shell feeling. The way table salt is made is the perfect example of this. You've got sodium, a classic metal, with just 1 lonely electron in its outer shell. It is desperate to get rid of it to become stable. Then you have chlorine, a nonmetal, which is just 1 electron short of a full shell. You can see where this is going, right? It's a perfect chemical match. So, sodium happily hands over its spare electron to chlorine. This transfer leaves sodium with a positive charge and chlorine with a negative one. And what do opposites do? They attract. They lock together in a really strong bond. And that right there is the fundamental dance. Metals are the electron givers, and nonmetals are the electron takers. Now, this whole tendency to give away electrons, it's not the same for all metals. Some are way more eager to react than others. We can actually rank them, creating a kind of chemical power ranking that lets us predict how they're going to behave. And here it is. This is the activity series. At the very top, you have these super reactive metals like potassium that will react with almost anything. And way down at the bottom, you have the really unreactive, chill metals like gold. The rule here is simple. Any metal on this list can kick a metal below it out of a chemical compound. So let's test that theory out. Here we have a regular iron nail in a solution that contains copper. Now look back at that reactivity ladder. Where are iron and copper sitting? Based on that ranking, what do you predict is going to happen here? And yep, a reaction happens. Because iron is higher up on the activity series, it's more reactive. It literally kicks the copper out of the solution and takes its place. It's a chemical switcheroo. That's why the nail gets this cool copper coating and the blue solution starts to fade. The latter works. Okay, so this isn't just some neat little lab trick. This understanding of reactivity is absolutely fundamental to our civilization. It's how we get pure metals out of the ground and use them to build our entire world, from a simple spoon to massive railway lines. To get pure metals, we have to process the rocks they're found in, which we call ores. For a lot of common metals, the very first step is to turn that ore into something called a metal oxide. We do this with a lot of heat, sometimes with plenty of air in a process called roasting, and sometimes with limited air and calcination. But the goal is exactly the same: create a metal oxide, which is the perfect starting point for getting the pure metal out.
And here's that displacement reaction again, but on a massive industrial scale. This is the thermit reaction. It uses superreactive aluminum powder to basically steal the oxygen away from iron oxide, which is pretty much just rust. This chemical swap releases an incredible amount of energy, producing molten iron on the spot. It's the perfect way to weld huge steel railway tracks together right out in the field.
But our mastery of metals doesn't stop with just pulling them out of the ground. For thousands of years, we've been mixing them together, creating totally new materials with properties that are way better than the originals. This is the amazing science of alloys. So, an alloy is just a custom mixture of two or more metals, or maybe a metal and a nonmetal. By mixing copper with zinc, we get strong, durable brass. By adding a bit of nickel and chromium to iron, we get stainless steel that's tough and doesn't rust. We can even engineer alloys for really specific jobs, like solder, which has a super low melting point that's perfect for electronics.
And you know, this science is far from new. The Iron Pillar of Delhi is a total marvel of ancient metallurgy. For over 1,600 years, it has stood outside, exposed to the weather, without corroding. It is a stunning testament to a mastery of materials that honestly still blows scientists away today. So we've gone from a snapping pencil lead all the way to an ancient rust-proof pillar. And we've seen that the secret to it all lies in that beautiful, invisible dance of electrons. This fundamental knowledge lets us design materials for basically any purpose we can dream of. So the final question is, as our understanding gets even better, what new alloys, what new combinations will shape the world of tomorrow?